Baron Martin Rees. He's been elevated by the Queen of England. He was also one of the youngest professors at Cambridge when I was in England for my first postdoc. And he has had an immense influence, as has Jim, on our understanding of the cosmos. And he's going to tell us about what we know, what we don't know, and what we may never know about cosmology. So, there he is. We can't hear him yet, but
back then,
Martin,
there were no instruments powerful enough to discriminate between these theories. But Jim Peebles has described how the subject's been transformed since the 1960s. When history of science gets written, that amazing progress, a collective effort, should be acclaimed as one of the greatest triumphs, up there with the standard model of particle physics, plate tectonics, and the human genome. My topic today is what we may learn in the next half century, and what we may never know. First, we'll surely learn more about how galaxies are structured, and how they form and evolve. Physicists who study subatomic particles probe them by crashing them together in accelerators. Astronomers plainly can't crash real galaxies together, but we can, in our computer, crash galaxies in a speeded up virtual world, in simulations incorporating gravity, dark matter, and gas dynamics. And this is an example. Everything in each galaxy exerts a gravitational pull on the others, causing distortions, tidal plumes, etc. By the way, Andromeda will merge with our galaxy in about 4 billion years. Andromeda is bigger, so financiers might deem this an acquisition rather than a merger. And if we look in the sky, we do see images like this. This is a pair of galaxies, and looking at them, it's clear they're going to merge within the next 100 million years. And we can test ideas of how galaxies evolve by observing eras when they were young. And the James Webb Telescope will study many deep fields like this, each encompassing a tiny patch of sky, but each revealing hundreds of galaxies, many so far away that their light set out when our universe was less than 5% of its present age. But first, let's address an issue that might seem puzzling. Our present complex cosmos manifests a huge range of temperature and density, from blazingly hot stars to the dark night sky. People sometimes worry about how this intricate complexity can have emerged from an amorphous, expanding fireball. It might seem to violate the second law of thermodynamics. But the answer to the paradox lies in gravity, which enhances density contrast rather than wiping them out. So any expanding patch that starts so slightly denser than average would feel extra gravity. A density contrast would grow until it eventually stops expanding and separates out, as in this movie. And that's why, incidentally, the small amplitude fluctuations in the nearly smooth early universe, revealed by the Planck spacecraft here, can be amplified by gravity into the conspicuous structures in our present universe. Here's a cosmic time chart. The processes that form galaxies involve messy gas dynamics and lots of feedback, like the weather does. That's in contrast to the early universe, the first few million years, which involve exotic physics, but where things are almost uniform. Werner Israel had a nice metaphor. He divided cosmologists into chess players who focus on fundamental mathematical physics, or mud wrestlers who try to understand the complexities of structure and evolution in the last 99.9% of cosmic history. I'm one of the few mud wrestlers here this week, where we can trace cosmic history on this time chart back to 1 second, where helium and deuterium fall. Indeed, I think we can with confidence back to about a nanosecond. That's when each particle had about 50 GeV of energy, as much as can be achieved by the best particle accelerators. And when, incidentally, the entire visible universe was squeezed to the size of our solar system. But fundamental questions like, where did the fluctuations come from? And why does the early universe contain the actual mix we observe of protons, photons, and dark matter? These questions take us back to the even briefer instance when our universe was hugely more compressed still. If inflation theories are correct, down from the solar system size to microscopic size. And lab experiments, of course, offer no direct guide to the relevant physics at these extreme compressions. So I put my hazard warning up about inflation theories. And here's another basic question. How much space is there together? How large is physical horizon? How large is physical reality? We can, even in principle, only observe a finite volume, a finite number of galaxies. That's essentially because, like someone in the ocean, there's a horizon around you. And unless we take a very non-Copernican view, there are galaxies which are already beyond our horizon. And in our accelerating universe, we can never even in principle observe them. There's no perceptible gradient across our universe from one side to the other. And that suggests that it extends probably hundreds of times further than the region we can observe. But that's just a minimum. If it stretches far enough, then all combinatorial options could be repeated somewhere. Far beyond the horizon, we could all have avatars. Be that as it may, even conservative astronomers are confident that the volume of space-time we can ever observe, even in principle, is only a tiny fraction of the aftermath of our Big Bang. And there's something else. Some scenarios, like André Linde's eternal inflation, suggest that the aftermath of our Big Bang could be just one island of space-time in the vast archipelago. We're one Big Bang among many, as illustrated in this cartoon. And a challenge for 21st century physics is to see which branch of this decision tree is correct. First, are there many Big Bangs rather than just one? Second, if there are many, as in Linde's model, are they all governed by the same physics or not? Many string theorists argue there could be a huge number of different vacuum states, different vacuum energies, different microphysics, and different Big Bangs may therefore cool down differently. And what we call the laws of nature may, in this grander perspective, be just local bylaws governing our cosmic patch. If physical reality is like this, then there's a real motivation to explore counterfactual universes with different gravity, different microphysics, and so forth, to explore what range of parameters would allow complexity to emerge. This is what's called anthropic reasoning. And it makes some people foam at the mouth, I'm afraid. And some don't like the concept because it would render the hope for neat explanations of the fundamental physical numbers as vain as Kepler's numerological quest to relate planetary orbits to nested platonic solids, as in this rather nice old engraving. But our preferences are irrelevant to the way physical reality actually is. So I think we should be open-minded to the possibility of a fourth and grandest Copernican revolution. We've had the Copernican revolution itself, then the realization that there are zillions of planetary systems in our galaxy, and that there are zillions of galaxies in our observable universe. But we then perhaps realize that our observable domain is a tiny part of a far larger and possibly intricately diverse ensemble of universes. And we'd live not in a typical part of this multiverse, but in a typical domain in the subset which allows complexity to develop. And to address this question of the anthropic constraints on universes, we would need to know the probability distribution and the correlation between them of the different numbers that emerge in the different models. And that's a can of worms that we can't yet open. And it'll have to await huge theoretical advances. I should re-emphasize that we don't know if there are any other Big Bangs. But they're not just metaphysics. We might one day have reason to believe that they exist. Specifically, if we had a theory that describes physics under the extreme conditions of the ultra-early Big Bang, and importantly, if that theory had been corroborated in other ways, by, for instance, deriving the unexplained parameters in the standard model of particle physics, or predicting the mass of the electron, then if that same theory predicts multiple Big Bangs, we should take that prediction seriously. And incidentally, there'd be no reason to assign these other Big Bangs different epistemological status from the unobservable domains beyond our horizon in our own Big Bang. They're part of physical reality. We can't observe, for instance, the interior of black holes, but we believe what Roger Penrose says about what happens there, because his theory has gained credibility by agreeing with data in many contexts that we can observe. About 15 years ago, I was on a panel at Stanford University where we were asked how seriously we took the multiverse concept. On the scale, would you bet your goldfish, your dog, or your life? I said I was nearly at a dog level. Andre Linde, who'd spent 25 years already promoting eternal inflation, said he'd almost bet his life. Later on being told this, Steven Weinberg said he'd happily bet Martin Rees's dog and Andre Linde's life. Well, Andre Linde, my dog and I will all be long dead before this is settled. Indeed, some of the crucial physics could be just too difficult for human brains, just as quantum theory is for monkeys. It's conceivable that machine intelligence could explore the geometric intricacies of some string theories, and perhaps the computer could spew out, for instance, the right mass for the electron or other key parameters of standard model. If that happened, we'd then have confidence in the theory we'd fed into the computer and take its other predictions seriously. But we'd never have the aha insight moment, which is the greatest satisfaction for a theorist. Even worse, physical reality at its deepest level could be so profound that its elucidation would have to await post-human species. So I end with that thought, depressing or exhilarating according to taste. And with a quote from Hubble, a heavy smoker here, as you can see, who said, "Only when empirical resources are exhausted should we enter the dreamy realm of speculation." Thank you.